without further ado, I'll give you Professor Rob Fender. Thank you.
Thank you very much, Bruce. Earlier today, just a couple of hours ago, we opened the first UK LOFAR station just up the road at Chilbolton. I'm going to repeat the words that I used when we went through our brief ribbon cutting ceremony, which is that I'm very happy to be here presenting this stuff, because really it's been quite a long time. It's been 10 years that I've been involved in LOFAR myself personally, and it's been 5 years that a whole load of us together within LOFAR-UK have been trying to get to this point of being able to complete this station. The station was signed off today by Astron, so we officially have our UK LOFAR station, and the station will be connected to the network and connected to the Netherlands by the end of next month. So it's really a nice and very important step forward for us within LOFAR-UK. Okay, so the title of the talk is Transformational Science with a Revolutionary Radio Telescope. And what I want to do first is just address why this is a revolutionary radio telescope. What is so different about LOFAR? So many of you will have seen the pictures of LOFAR. LOFAR has two sets of antennae. The ones which most of you would have seen most pictures of are these low-band antennae, with a picture here of Derek Mackay, who's been instrumental in getting the station at Chilbolton working. These antennae themselves, they just have these bits of wire which are very, very simple. They just, they're just sitting there collecting the signals coming in from space. But it's basically the addition of enormous computing and data transport power to this network of antennae that allows us to really do this transformational science. And it's revolutionary for various reasons. First of all, it has an enormous field of view. Now, the story of the history of astronomy in most cases has been that as we go to more powerful instruments that are more and more sensitive, we get smaller and smaller fields of view. As I'll illustrate to you in a moment, the field of view of LOFAR is in fact very, very large indeed. It's enormous. It's larger than the field of view you get with a small telescope in your own backyard. And that makes LOFAR an extremely fast and powerful instrument for doing astronomy. Not only does it have an enormous field of view, but it can have multiple enormous fields of view. So there's this amazing thing about LOFAR, which is basically these antennae sit there, they never move, they just sit there, these dipoles sit there connected to this computer, which then is connected to the supercomputer in the Netherlands. Without moving, they're able to point at different points in the sky at the same time, and multiple different points of view at very, very short notice. Beyond this, they're actually able to look back in time, okay, which sounds a bit ridiculous, but in fact, if you store the raw data at a LOFAR station and you get an alert from another telescope, you're actually able to say, okay, I'm going to find out what was happening over there about 5 minutes ago. And this is something you can do in software with LOFAR. And as I've already said, this really is all down to the fact that enormous advances in computing and data transport power have allowed us to make these great advances with LOFAR. So this is a map of Europe with, in green, you won't be able to see it very well, the LOFAR stations which are currently active or under construction marked out. Here is the Dutch core, here's the Chilbolton station, Swedish station, German stations and French station. And all of these stations individually are transporting 3 gigabits per second continuously back to this supercomputer here in the Dutch core of Astron, Dutch core of LOFAR, led by Astron, which allows us to produce these amazing images. So how does this work? This is the most technical slide of the entire presentation, and it's not too technical. This represents LOFAR. These are 2 LOFAR dipoles which sit there on the ground not moving. These are 2 traditional radio dishes, the kind of thing that you're used to seeing and the kind of thing that there's a nice example of at the Chilbolton site itself. So there's an interesting thing over here you want to look at. With LOFAR, what you do is you introduce some delays in software which allow you to look in that direction. With your traditional dishes, you have to get the dishes which have a very small field of view and you have to slew them around until they're all pointing in the same direction. If you then want to look at an even more interesting source in another direction, With the traditional dishes, you then have to get them, put a command in, and you have to slew them round, and this can take several minutes, of course, and if you do it regularly, basically adds a lot of overhead to your observing program. With LOFAR, you just introduce delays and change the delays that you introduce in the software, and suddenly the whole array is focusing in that direction rather than that direction. And you can do this in principle on sub-second timescales, and you can do it in multiple directions at once. You can introduce different delays for different bands within the whole LOFAR bandpass, and have one frequency range pointing over there and one frequency range pointing over there. So as I said, you can look in multiple directions at the same time, and by storing the raw data from LOFAR, which actually at the moment we are doing, but on very small timescales, with RAM memory chips actually at the antennae, you can in principle look back in time. And in the future, we'll be able to upgrade this RAM at the antennae so that we can actually store more and more of this raw data, and we may get a signal from some other astronomical facility saying something interesting happened over there 1 minute ago, and we may be able to take this raw data, add the delays to it, and actually focus, if you like, back in time on that part of the sky to see what was happening there. So as I've said, these enormous fields of view are really a fundamental part of why LOFAR is really very revolutionary. What I'd like to do now is to actually use this planetarium in which we're sitting to actually illustrate the enormous fields of view of LOFAR. Even the astronomers who have been working on the project won't really have appreciated, I think, to date, how large these fields of view are. And before you see the fields of view, I'd just like to remind those of you who are not astronomers that some tiny little dot in the sky like that is the typical field of view of a large astronomical facility, for example, an optical facility. In contrast, the LOFAR fields of view are much, much larger. This is an example of what LOFAR can do. So here we have, for example, 4 LOFAR beams, one of which is centered on the Andromeda Galaxy. A single beam from LOFAR can cover the entire Andromeda Galaxy, and we could, for example, tile 3 more beams around it, use them to sweep the sky every day. As well as focusing over here, we can focus another beam here, for example. There may be another interesting astronomical object here, here, and here, and we can move these beams across the sky as fast as we want to. This is really a revolutionary step forward for astronomy, and as I say, is entirely enabled by clever software and data transport. Okay, back to the science, which was the second part of the talk. That's why LOFAR is revolutionary. What is the science that LOFAR is going to do? Well, the science for LOFAR, somebody asked me earlier today in an interview, what kind of distance scales are the interesting objects that LOFAR is going to study? Well, LOFAR will basically study all distance ranges that astronomers are interested in. Close to home, LOFAR, as I'll show you in a moment, is an extremely valuable tool for monitoring activity on the surface of the Sun. Okay, strong activity on the surface of the Sun tends to be associated with low-frequency radio bursts, which themselves may be associated with other interesting phenomena. At the largest distances, LOFAR will be a fundamental tool for cosmology, for actually understanding how our universe has evolved over cosmological timescales over the last 14 billion years. What is the distribution of matter within the universe, and how did the universe become hot again during the so-called epoch of reionization? And the data we get from LOFAR will really help us to probe cosmology and understand our universe at the largest scales. We will be able to map the history of the growth of black holes basically through the entire history of the universe. The very first supermassive black holes through to smaller black holes in the present-day universe, we will be able to observe them by the signature radio emission they produce. Even closer than the Sun, we can see radio bursts in the Earth's atmosphere when very high energy particles enter the atmosphere and produce what's so-called secondary particle cascades. So we can actually do particle astrophysics by observing radio bursts as particles interact with our own atmosphere. And as those of you who were at the site at Chilbolton today would have seen, one of the key things you can do in radio astronomy, and in particular when we're commissioning and developing LOFAR over the coming months, is pulsar astronomy. The sky is full of pulsars, which are rapidly rotating neutron stars, so something about the mass of the Sun compressed to only 10 kilometers across, and these produce regular bursts of radio emission. And in the future, by studying large numbers of pulsars, we'll be able to directly test theories of general relativity. Okay, so there have been some results already for LOFAR. One of the nice things about LOFAR is that it's sort of a modular radio telescope. Again, as those of you who are out at Chilbolton today can testify, with a single station on its own you can do astrophysics. You can observe a pulsar and track it with a single station. As you add stations together, basically as you complete a station and add it to the internet so you can send the signals back to the Netherlands, you add more and more collecting area and you add more and more angular resolution to the array. So even though LOFAR isn't quite complete yet, we're able to do lots of science already. So what you see here is a sequence of 1 second images of the sun obtained with LOFAR. So these are low frequency radio images where you basically see a sequence separated by 1 second, and what we see is that around here there was a radio burst which we can localize to some particular region on the sun. These radio bursts we know already are probably associated with so-called coronal mass ejections, which in some cases actually directly interact with the Earth's space environment. So the importance of this kind of monitoring is clear. On a larger distance scale, we are able to observe the environments of supermassive black holes. So this is a very, very bright source in the sky. It's called 3C196, and it lies about 7 billion light years away. This is an extremely massive, millions of times the mass of our sun, an extremely massive black hole which produces strong radio emission. And this is a very nice illustration of the extra science you can do with LOFAR by bringing in the international stations. So this is the image you make of 3C196 using only the Dutch LOFAR stations, and it's not particularly spectacular. You measure a nice radio flux, which in itself can do some science for you, but you don't really see any structure. Simply adding in 3 of the German LOFAR stations increases the angular resolution by a factor of 40 for LOFAR, and suddenly you're able to resolve all sorts of structure. And what this structure tells you is the past history of how relativistic outflows from the black hole have interacted with the surrounding environment, and that in turn ties into questions of things like the growth of galaxies, etc. Adding in Chilbolton, the UK station, to the LOFAR array, which hopefully will be on a timescale of about 1 month, will actually further allow us to double the angular resolution achievable in these images with LOFAR. Studying pulsars has been one of the fundamental sort of tools for commissioning LOFAR, and as I said, eventually will lead us to being able to test general relativity. So this is just a couple of examples of what LOFAR can do and the scientific promise of LOFAR for pulsars. This schematic here actually hides the fact in a way that there are 2 bits of real data here. So this is real data from this pulsar, and this is real data from this pulsar, and these 2 pulsars were observed simultaneously with LOFAR. So dual beaming, multi-beaming with LOFAR, taking real data in 2 fields, many degrees apart, is actually already working for LOFAR and can be demonstrated with pulsars. Furthermore, in the broadest band pulsar observations ever taken, simultaneously with 2 large dishes, simultaneously with LOFAR high and low band antennae, we can see how the structure of the pulse itself changes with frequency, which tells us something about the structure of the magnetic field very close to the neutron star. And again, this is a fundamental test of our understanding of how these beasts work. Very happily, we found out last week that the Chilbolton LOFAR station does actually work. Due to primarily an enormous amount of work by Aris Karastergiu, we were able to get the first astrophysics through the LOFAR station. So although it was only signed off officially this morning, or midday today, we're actually already taking astrophysical data with the Chilbolton station. These are the pulse profiles of 2 pulsars up in the sky. And there's a very nice thing here, which is that a piece of software developed for another but related project, the Square Kilometre Array, is actually useful in actually helping us to process more efficiently the data which is coming through the LOFAR station. So 2 sub-projects which are specifically led by the UK are already being demonstrated to be enhancing the data that we're getting from a LOFAR station. So I just want to end there and end by thanking all the university partners who, some of whom 5 years ago, on the basis of a reasonable talk by myself and by others, agreed to put £50,000 into a pot with the aim of building a LOFAR station in the UK. For at least 4 years, some of these people didn't know what happened with their money. Well, finally, we've got there and we have a UK station. Thank you very much.